flight, and this is a relatively short overview of analysis of variance, or ANOVA for short. And what we want to do when we talk about ANOVA is essentially we're testing between two groups to identify whether these two groups are different from each other based on some criteria. So we'll take two different populations. Oftentimes we form a hypothesis and then do a hypothesis test to confirm or refute our initial assumptions. Okay, so we're going to need at least two variables, one of which needs to be categorical or a grouping variable. The second or other variables should be metric or continuous, so they should be ratio or interval data. And we'll walk through an example to look at some of this. The metric data, we might call those factors. That's another term that you're going to hear. But essentially, we look to take our subjects and then split them up into a couple different groups. And by splitting them up, we are able to identify key differences between them. Let's do a little bit of an example just to walk through what we might expect. All right, so suppose we took a random sample of people and measured their height. And we decided, well, okay, everybody averages to be a certain height, but we hypothesize that maybe gender has an influence on height. So we take this idea and we split our data between men and women and look at the average height for the men and average height for the women. And we form a hypothesis. And so in this case, our hypothesis is going to be that they are equal in height. Not that they're different in height. That's not the way we form hypotheses. Hypotheses would state, in this case, that they were equal in height. And we're going to either reject that hypothesis. If we rejected that hypothesis, it would mean that they are unequal in height statistically. If we fail to reject the hypothesis, it means that they are statistically the same in height. And sometimes we might say accept the hypothesis. Technically, you're not supposed to do that. You're supposed to fail to reject it. But that's getting petty. That's a minor issue. So let's take a couple looks at some graphs and just kind of see how this goes. If I went back, I could just see here how we have two different means, the means of the men versus the means of the women. We have a 60 and a 70. And again, we kind of average those together to get 65 maybe if we have an equal sample between men and women, an equal sample size. So just bear that in mind, and I'm going to put up a couple different graphs. These are hypothetical distributions. One distribution, the blue line would be, and it's the line on your left, the curve would be women, and then the curve on the right, the greenish looking one, would be the men. And I'm going to see that in each case, the mean for each of these draws will be 60 for the women and then 70 for the men on their height. Now again, these are just two hypothetical distributions or samples, right? And now we want to just kind of compare and take a look at both of them and make some looks. So one thing we can say is, well, look, it appears as though the group in the data in A, it appears like there's less variability. And by that I mean you can look at the distributions and they're closer together. The men and the women's curves are more peaked and they're closer together. There's less spread between them. On graph B, they're spread out further. So there's more variability, there's more distribution. And also, at the same time, we look and we can kind of see that there's an overlap between the men and the women's heights, in both cases, A and B. But in B, the overlap's much greater. That's significant, and that's important, and that's what we want to kind of key in on here as we move forward a little bit. Okay, so let's just again say that we're taking these random draws, and we look at group A. If we took a random draw or a random sample from a distribution in graph A, the odds of grabbing a person who falls between the two, so either a woman or a man who falls in that middle range, the odds of that are less in graph A than the odds of choosing the same type of person in graph B. In other words, that overlap, because it's larger, it increases the probability of an inclusive or an inconclusive result, right? Because if we drew a random person from chart graph B, the odds of choosing somebody from that middle portion, it means it could be a man or a woman. There's not, like, it doesn't distinguish. Whereas over in A, chances are going to be a lot less that will happen. And so in words, one of the things that we can say is, if we set a significance level, again, remember our hypothesis is that men and women both have equal heights. So let's say our significance level is 10%, 0.10. And so basically, if I took a random draw, the question that we ask when we set that significance level is, do we have a better or worse chance than 10% that we'll draw a sample from the shared space? So again, my question is, when I draw a sample, what is the probability that that sample is going to come from the shared space versus the non-shared space? And in this case, if the significance level is 10, we ask, is a chance greater than 10 or less than 10% that I'm going to draw from that space? So if you're drawing from the graph on the left, the A graph, then chances are much, much less that you're going to draw from the shared space. Whereas if you are from the distributions that are in graph A, chances are much, much greater, and probably greater than 10%, that you'll choose somebody from the middle space. Okay, so using that and keeping that in mind, we would then form and let this help us identify how to answer or how to satisfy this hypothesis. Okay, so now remember, our hypothesis is that they are equal in height. So if we would reject that hypothesis, if we saw graph A, because it seems as though there are two different distributions that don't share a lot of space or share a lot of commonality with each other, share a lot of variance maybe. Graph B, however, because there's so much shared space, you really can't distinguish one group from the other with certainty. Yes, they have a different mean, but just because their two groups have a different mean height doesn't mean they're statistically different. And that's the key. And there's too much variation, too much variance that's shared in graph B to say that these two groups are statistically different. In graph A, you have a much better chance of drawing either a male or a female depending on that draw. Okay, so or somebody from outside that shared space. Okay, so this is kind of the idea of an ANOVA. We want to test and we want to identify how different these distributions are from each other, and if they're different enough, then we'll show that in our test, like graph A. But if they're not different enough, then we won't be able to distinguish one group from the other on whatever this criteria is. In this case, the criteria is height. And so that's the idea of an ANOVA. That's what we want to show group differences. You might think of this as a between group t-test. It's not, but you might think of it as one. And one of the things is ANOVAs allow us to introduce multiple levels. So in this case, we have men and women. But what if we had men, women, and non-binary, or men and women and some other categories involved? Or maybe we did something where we'll have an example where maybe we do freshmen, sophomore, junior, seniors, and we want to look across 4 groups instead of just 2 groups. Between group t-tests allow for 2 groups. ANOVAs allow for more than 2 groups if you should want to do that. So that's good. There's also many, many variations of ANOVAs. For instance, if you have, if instead of you have metric data, you had, or instead of categorical groups, you had metric data, you could do an ANCOVA. That's a little bit of a different thing. There's a C in there, an ANCOVA. If you have multiple metric variables, so we have a group, 2 groups, and then we have lots of metric variables, so not just height, but maybe height and weight and age and some other things like that, then we can do a MANOVA, multiple analysis of variance, MANOVA. Okay, so again, there are extensions to this that could certainly be done, so there's a lot of flexibility there that we could kind of look at. So here's another 2 examples. And this is with SPSS. So SPSS is a software program. Once you have your data prepared and in the software, then you can do a ton of analysis. So there's going to be the 5 or 6 steps here that you see to kind of get into the proper window. So you can do ANOVAs. So, but in SPSS, what you want to do is go to the Analyze ribbon at the top. There'll be an Analyze drop-down box, and you want to go into Compare Means. And when you are in Compare Means, and again, it'll be another drop-down box, you go to One-Way ANOVAs. One-Way ANOVAs, okay? And then you're going to go through and add some items to that box, and we'll look at that here in just a second. So again, after we go to Analyze, Compare Means, One-Way ANOVAs, this box is going to pop up, okay? And it's not complicated. It's not really sophisticated. Here we have some data where we have satisfaction, and there's an average satisfaction score. And then under version, we have and again, this is a grouping variable. There's only 2 options. It's either going to be a rainy day or a sunny day in this data set. 2 options. And so we're going to compare respondent satisfaction, and this is to a service, on whether, how they are satisfied when they were asked this question on either a rainy day or a sunny day. And then we're going to see if satisfaction is in fact different. So you see where satisfaction, the variable, the scaled variable, goes into the dependent list. Don't get too confused or worried about the word dependent there. Just place it in there. And then second, we put the category version in the factor list. On the right-hand side, you're going to see contrast, post hoc, and some other things. You can get into those if you want to do some other ask the software to do other stuff for you. We don't really need to right now, so we're good to do that. We would just click OK at this point, and then move on to the next screen, which is a output file. So this is the output that you're going to see, and in this case, the top box gives us our descriptive statistics. So things we're going to look at right here are probably going to be variance and mean, and in particular mean. So mean means it's the average score of satisfaction for people who took the survey on rainy days and people who took the survey on sunny days. And this was in the process of the respondents receiving a service. This is in a service environment. So they're receiving a service and they're asked to do a survey. Happens to be raining one day, and the average satisfaction is 3.62. On sunny days, same test, same sample, same like idea. Sunny day, the response is 3.88, almost 3.89. And so the question here is, is that a big enough difference? Is that a big enough or significant enough of a difference between these two? So again, we know that based on this, people respond more positively on a sunny day than they do a rainy day. Question is it a significant enough difference to say that we have two separate groups that can be defined by weather, right? Or response by weather? Can weather be a differentiating factor for us? Basically, that's what we want to know. So we look down below. We look at, in this case, the F statistic, and we see that it's 0.043. Typically, we look for a 0.05 or lower. That's usually the benchmark, and we want it to be low. The lower, the better on this. So based on this data, based on this sample, people who respond to service environments on sunny days are significantly happier or more satisfied than people who respond to the same survey in a service environment on rainy days. So if you want to do your evaluations, if you want to get your customer satisfaction scores up, hope for a lot of sun, I guess. That's the takeaway there. Okay, second example, same data set. We'll do the same thing. Again, analyze, compare means, then go to the one-way ANOVA, okay? And you'll get this box. In this case, we're going to do average community or brand community score. So there's this thing called brand community. When people are part of a brand, they feel like other people should be part of that brand too. And so brand community then is the scale metric. And in this case, we're going to do gender, okay? And we have males and females. So it's two cases. And we have this idea of, do you feel part of a community or not? Again, this is the same service environment that we just saw. So we'll pull this up, see what the results are. And again, we'll look at the means. The standard deviations are very, very close, and they're close to 1, so that's good. So that's kind of a good sign of your data. And 3.09 is the female response to their degree in which they feel like they're members of a community. 2.71 is the response for males. So we see that there's a difference. Again, though, we want to test to see if there's a significant difference. And certainly there is 0.017. It's much less than 0.05, which would be, again, the cutoff that we would use. And so we'd say, yeah, they're statistically different. So females feel, in this sample, feel more attracted to or part of a community of either the brand or the service than males. Okay, so this is a step through and just kind of walk through ANOVA. And again, the key thing here is we can build on this. It doesn't just have to be 2 levels of the factor. We can have multiple levels of a factor. And again, that's something that a simple t-test won't do, like between groups. So this adds a lot more creativity or power, if you will, to the things that you're able to do. Okay, so again, hope you enjoyed. Please feel free to study this and practice this in SPSS. Thank you.